Okay, now the last pressure we'll speak about here is the transpulmonary pressure. This is essentially the alveolar pressure minus the intrapleural pressure. This is the force for distension. This is what keeps the lungs able to distend to accommodate air. So increasing in the transpulmonary pressure is what allows the lungs to distend. If we drop our transpulmonary pressure by decreasing the intrapleural pressure, we lose this force for distension. Okay, really, really important. So this causes the lungs to expand, which increases the volume. And we'll talk about how volume and pressure are related coming up here. But basically, the alveoli expand when we increase the volume, therefore decrease the pressure, and that facilitates our pressure gradient, right, from high to low pressure. But we can only decrease the pressure by increasing the volume. Okay, and that will make more sense as we go along here. Okay. Any questions so far? Any confusion so far? Okay, so let's kind of recap some of this here in a way that makes a little bit more sense. And then we're going to move on to define how we actually get these pressure gradients, okay? All right, so we're speaking about pulmonary ventilation. And we're going to describe the two phases of pulmonary ventilation. So expiration, and then we'll look at inspiration over here. Okay, let's just draw the airway here. Let's draw our lungs, nice and inflated. This is going to get a little complicated and some bad drawing is involved, right? But our lungs, okay, not too shabby. And so we're going to start by just reminding ourselves of two important principles here, okay? So the first thing is that the driving force, let me see this, okay. Oops. Okay, so the driving force for ventilation is our pressure gradient, okay? And that pressure gradient simply means atmospheric pressure minus alveolar pressure. Okay, that's the first important thing. The second thing we'll say here is that at rest, so at the end of a full expiration, which is at rest, the atmospheric pressure is equal to the alveolar pressure. Okay, so we have a gradient which creates airflow, and at rest we have no gradient because these two pressures are equal, and so we have no flow. All right. So let's start with our first pressure. So we know the first pressure is the atmospheric pressure. This is out in the air that we're breathing. We cannot manipulate this pressure. What we can manipulate are our internal lung pressures, okay? So this is equal to 0, and that is the relative value. Oops. then what did we say that was at sea level? Yep, 760 millimeters of mercury. And that was the absolute value. Okay, so that's our first variable, the atmospheric pressure. Now, during inspiration, the alveolar pressure, so the pressure inside the alveolar here, the alveolus here, is going to be greater or less than this zero, greater or less than the atmospheric pressure for inspiration. Think about that pressure gradient. It's going to be less, yeah, so it's going to have to be less than that zero. So it's going to be, let's say, -2 millimeters of mercury. And if we take 760 and we subtract 2, that's about 758 millimeters of mercury. Okay, just to put the absolute value as well. Our intrapleural pressure, which is the pressure in the pleural cavity, has to be less than the intraalveolar pressure. Okay, so it's going to be more negative. Again, that's what's keeping the lungs inflated. So we'll say that's about -6 millimeters of mercury. And again, doing some math here, that's going to be about 754 in terms of the absolute value there. Okay, so everyone understand the inspiratory part of this. The alveolar pressure needs to be less than that zero, and the intrapleural pressure needs to be less than that alveolar pressure. Okay, it needs to be negative. All right, okay. Let's look at expiration. Yep. Sure. Oops, that's a mistake there. So this should be 754. Okay, make sense? My mistake. So 754, which is -6 relative to our 760. All right, everyone still with me? Any other questions? Okay, now during expiration, what do we want our alveolar pressure to be? More or less than this zero? So we're trying to move air out of the lungs. We've got 0 in terms of our atmospheric pressure. The pressure in the alveoli is going to be more or less than that. It's going to be more, right? So it's going to be higher. So let's see, our alveolar pressure is +2 millimeters of mercury here. And then that we can say is about 762. Okay. And then our intrapleural pressure. Questions? All right, so our intrapleural pressure needs to also be less than our intraalveolar pressure, all right? So that's going to be about -2 at this point. Okay. Which brings us to about 758 millimeters of mercury. Okay, so let me pause here. Everyone understand how we get these values? Any questions here? Okay, and then these can change throughout respiration. These are not fixed values, right? Air is moving in, so we're gaining a gradient, and then we'll eventually lose that gradient as air moves out. So this is not a fixed value. This is just showing some references to how we acquire that gradient that we're speaking about, okay? All right, let's speak about the transpulmonary pressure here a little bit. So the transpulmonary pressure, we describe it as being the distension force, so the force for distension. Right, we said that was the distending pressure. And that was basically the difference between the alveolar pressure and the intrapleural pressure. Okay? Difference between the alveolar pressure and the intrapleural pressure. And that is going to be -4 millimeters of mercury at rest. right? So -4 at rest. So it goes from being -6 during inspiration, it gets to -4 when we're at complete rest, and then eventually it gets to -2, then back to -4 to -6, and so on and so forth. But it must always be less, the intrapleural pressure must always be less than the alveolar pressure. So this value must always be a negative value, okay? All right. What questions do we have at this point? Other than the scratchy handwriting, what questions do we have? Okay, so let's make some general principles here. We said that in order for expiration to occur, the atmospheric pressure must be less, or we can say the alveolar pressure must be greater than the atmospheric pressure. In other words, the alveolar pressure must be a positive value. Okay? So alveolar must be greater than atmospheric, and alveolar must be a positive value. And the reverse is true. In order for inspiration to occur, the atmospheric pressure must be greater than the alveolar pressure. Another way of saying that is that the alveolar pressure must be a negative value. Okay? All right. Now, what we're going to move on to speak about from this point is how we get these pressure gradients. So we spoke about the pressure gradients themselves. How do we actually get these gradients? We cannot manipulate the atmospheric pressure, but we can manipulate our alveolar pressure, our intrapleural pressure, and that's how we can manipulate the gradient to move air either in or out, depending on what we want. And the way we do that is by manipulating the volume of the chest cavity. So as you can see here, during inspiration, the diaphragm is nice and flattened out. And so that's a really big thoracic cavity. The volume of the thoracic cavity is large at this point, and so the pressure is lower. We'll talk about that relationship between volume and pressure. But a larger volume equals a smaller pressure, and here we want a smaller pressure to drive that gradient. In expiration, the diaphragm relaxes, it's no longer flattened out, and so we make the thoracic cavity smaller, and so we decrease the volume of the thoracic cavity, which increases the pressure of the thoracic cavity of the lungs. And again, that is creating the environment to drive air out. So in order to manipulate the pressure, we must manipulate the volume